This seminar will introduce an example of chassis heat dissipation design in a power module power supply. First, I will explain chassis heat dissipation that uses a chassis. This is a method in which the power supply is attached to the equipment chassis, and the heat generated from the power supply is dissipated externally through the chassis. Power supplies that can dissipate heat from the chassis are those that have a plate for heat dissipation. The advantages are that it can be made into a sealed chassis that allows heat to escape through the chassis, so no dust can enter the equipment, and it can be designed to be quiet. But it must be noted that the heat dissipation capacity depends on the chassis size and material. Next, I would like to talk about chassis heat dissipation design and the types of power module power supplies. So let's start with the power module power supply. This image shows an example of a configuration using a power module power supply. The types available are distributed, multi-output, AC front module, and high voltage input module configurations, and space-saving, single output, AC-DC module configurations. This power supply can be used with various power supply configurations to meet equipment requirements. I would like to go over some notes on chassis heat dissipation. Chassis heat dissipation capacity varies depending on the shape, material, and thickness of the chassis. Chassis A is a thin sheet metal chassis. Chassis B is a thick sheet metal chassis. And chassis C is a thick sheet metal chassis that includes fins. For the same internal power supply losses, chassis C has the lowest power supply temperature. The following are the design conditions for examples of chassis heat dissipation design for power module power supplies. In this example, the power supply TUNS 1200F28 is mounted onto the evaluation board, which is then configured to dissipate heat using a chassis heat sink. We will use thermal interface materials and grease to check if up to 1200 watt can be used with this chassis. First, let's look at a thermal network model of the chassis heat dissipation. This is a breakdown of chassis dissipation. Heat generated from semiconductors and other components inside the power supply is dissipated to the baseplate, thermal interface materials, and chassis. Let me explain by breaking it down into 3 steps. Step 1. Obtain internal loss or efficiency data. When calculating internal losses, efficiency data is required. Efficiency data can be found in the product specifications and catalogs of power supplies. It shows the data at rated input-output. If you need efficiency data at a light load or half load, please download the property data from the COSL website and check the efficiency and load property data. Here, the input voltage is assumed to be a 100 volts operation with a rated load, so the efficiency data is calculated using 89%. Step 2. Thermal resistance datum of the thermal interface material. Thermal interface materials TIM can be placed on heat dissipating contact surfaces to reduce thermal resistance and improve heat dissipation efficiency. Heat dissipation contact surfaces, such as power supply baseplates and heat sinks, are made of metal, so they are always uneven surfaces. And when those surfaces are in contact with each other, air gaps are created, resulting in unstable and large thermal resistance on the heat dissipation surface. By placing a soft material, such as grease or a sheet, between the power supply and the heat sink to fill the gap, the thermal resistance of the contact surface, that is, contact thermal resistance, can be reduced. It is not easy to obtain an accurate value for contact thermal resistance because it depends on contact pressure and hardness of the contact surface material, as well as material differences. Since heat dissipating grease is used in this example, the contact thermal resistance is postulated to be 0.5. The thermal resistance status of the contact surface is 0.0049 degrees Celsius per watt from this equation, and the thermal resistance datum of the thermal interface material is 0.058 degrees Celsius per watt from this equation. Step 3. Thermal resistance theta C of the chassis. Using the volume of the heat sink to be used in the chassis, Determine thermal resistance theta C of the chassis, to be used from the envelope volume thermal resistance graph. The thermal resistance was calculated from the intersection of a chassis volume of 4.05 by 106 mm3 and the graph. The thermal resistance of this chassis will be 0.37 degrees Celsius per watt. Output power available. Determine the power that can be output using the efficiency and thermal resistance calculated earlier. Under the environmental conditions of a base plate temperature of 85 degrees Celsius and an ambient temperature of 20 degrees Celsius, output power results in an available power of up to about 1200 watts. This is the result of checking the output power. This chassis was able to output 1200 watt at an ambient temperature of 20 degrees Celsius. In the case of smaller chassis parts, the output was 560 watt and 600 watt, but both were able to output 1200 watt by cooling the chassis with a fan. This is the summary of examples of chassis heat dissipation design in power module power supplies. Chassis heat dissipation is affected by the specifications, dimensions, thickness, and material of the chassis to which the heat is dissipated. Thermal interface material is needed between the chassis and the power supply so that they are closely connected. When calculating internal loss, please check not only the electrical property data in the specifications, but also the technical data and property data. Thank you for watching.